Hello, my name is Tim Clark, founder of Corazon Oilfield Services. Welcome to Coring 101, Episode 4, Reservoir Simulation. This episode comes in courtesy of Nabi Mirzai, independent upstream oil and gas consultant and technical advisor, who's kindly allowed me to use two of his articles on reservoir simulation to create an episode. First, we're going to look at a bird's eye view of the reservoir simulation process, and then uncertainties in reservoir simulation. Firstly, the bird's eye view. Reservoir simulation of a field is the outcome of geosciences and reservoir engineering studies. The constructed model is prepared according to geosciences and reservoir engineering principles. The model is changing all the way through with the history matching and simulation process. The model must stay coherent with the aforesaid principles during such process. As such, changing the matching parameters to make the model matched with observation data must keep the model organic and coherent with such principles. Only such history matching models may be trusted as an appropriate tool for predicting future reservoir performance. Put the reservoir simulation in such driveway the following points are highlighted. 1. Conduct close review of the documents on reservoir engineering, geosciences, field performance reports, information and data to find or confirm reservoir initial state characteristics, the main drive mechanism and at least two other acting drive mechanisms, major flow regime and the controlling parameters, major rock types feeding the wells, facies changes, faults, lineaments, barriers, sweep areas, etc. Reservoir sectors or compartments, reservoir fluid calibration regions, layer contributions, etc. Evaluate uncertainties of data groups such as permeability, reservoir fluid properties, relative permeability endpoints, and so on. Conduct reservoir engineering analogy to conclude key factors having a major effect on reservoir production mechanisms and reservoir fluid flow regimes. Make sure well test interpretations have been conducted with the same basis and convention. Give a red light to interpretation results done by different specialists, different software packages, or different companies. Understand well test results represent which rock group, layer, or region. Conduct quality control and inspection process to make sure reservoir initial state characteristics is correct. To make sure reservoir initial state characteristics are correctly determined in reservoir engineering and correctly consistently implemented in the model. Use the above conclusions to arrange the following. Propose a roadmap for implementation of reservoir simulation processes, including global strategic plans for history matching, sensitivity analysis, prediction, reporting, and presentations. Learn from above and in the context of the roadmap, prepare a strategic plan for history matching, an order of history matching processes such as reservoir global matching, material and energy balance, well modeling, region or sector modeling, how to act globally and hit local targets, how to consider regions without wells when pursuing HM objectives, make a priority list of matching parameters, plan methodologies for tuning, propagating and validating history matching parameters, plan procedures for implementing history matching strategies and methodologies such as selection of rock types, such as selection of type of correlations to propagate rock permeability, relative permeability endpoints, and so on. And the best time for starting performance prediction processes before completion of history matching, plan strategy, methodology, and procedures for sensitivity analysis, well planning, and performance prediction scenarios, plan for documentation, interim reporting, and presentation. And that was a quick bird's eye view of the reservoir simulation process. Now we're going to look at uncertainties in reservoir simulation. Reservoir simulation models evolve from static models, which themselves are the result of the assessments of discipline models. The discipline models are studies including geophysical, geological, petrophysical, and different data evaluations and studies in reservoir engineering. The combination of the results of such sets of studies and assessments are organized in the context of the reservoir static models. Recurrence and well data are added to the static model to form reservoir simulation models. The reservoir simulation model may be run in a dynamic state. The complexity of the resultant model grows during its evolution from initial geophysical model to a 3D geological static model and makes another leap ahead when it is evolved into an RSM. During the preparation of such datasets, the objective is to have each part of the dataset to be representative of the prevailing phenomena. Each piece of such a complicated puzzle bears uncertainties in various aspects. Considering a model as a discrete dataset represented by grid cell properties, one must take into account two additional sets of approximations and limitations affecting uncertainties of the model. The first set refers to the way such representative values are calculated or evaluated, and the other issue is related to the limitations of software, hardware, time, and budget, actuating new constraints on the model. Consider the reservoir simulation as inverse problems. Considering the reservoir simulation as inverse problems, theoretically, reservoir models may be matched by different combinations of parameters to the same observed data, such as well BHP, water cut, and so on. On the other hand, there is only one combination of the data that has initiated the observed data. Getting closer to the actual model, the main challenge is to understand the nature and sources of uncertainties and to have an appropriate methodology for handling such uncertainties. Oversimplifying such a complicated puzzle to find a mathematical combination of some history matching parameters to match the observed data could guarantee that predictions may not come true. Reservoir simulation modeling is the only tool for predicting reservoirs' future performance. Irrespective of the uncertainties of reservoir modeling, there is no better way than using such models for predicting or estimating the reservoir production potentials and future performance. To understand the elements of uncertainties in reservoir simulation, one may take a tour walking through the prediction of such models. Reservoir models are the result of multidisciplinary studies, all associated with different degrees of uncertainty. To conclude an RSM, 5 independent upstream disciplines, geophysics, geology, petrophysics, reservoir, and production engineering are incorporated, while each discipline model consists of several independent and uncertain data sources. Discipline models, when built, each need to undergo quality control and consistency checks to make sure they are sound and consistent before joining in the geological model. When such data joined in the geological model, additional consistency checks and quality control are necessary to make sure that the discipline data is still consistent and in agreement with other discipline information in the model. In this context, appropriate geological modeling workflows need to be established and utilized to generate a 3D static geological model by combining structure, property, saturation, and fault data. While putting discipline models together one by one, the consistency and coherency issues surface, showing the necessity for quality control of the generated compound model at each stage of development. By running geological modeling workflows, the completed geological model again needs to undergo quality monitoring and validation to make sure that the combination of different discipline data is well organized in the model and the model is sound, consistent, and meaningful. Only the confirmed static geological model may be utilized as the base for building dynamic reservoir simulation models. The dynamic reservoir simulation model is established by utilization of static 3D geological models and incorporating well and time-dependent data from reservoir and production engineering disciplines. The dynamic model must undergo quality control and validation, which is performed in 2 distinct stages. At the first stage, the model is quality controlled and validated in the static mode, and at the second stage is validated in dynamic mode. The first stage is called model initialization, and the second is called model validation, or so-called history matching process. The major quality control and validation of the reservoir simulation model is accomplished through the history matching process. History matching is an important part of the reservoir study, taking at least 30% of the whole project time in most cases. Unlike quality controls and validation processes in the static mode, the model in history matching mode is interactive. The dynamic model is capable of calculating some dependent data arrays provided that the pertinent information is provided. Production data is given. Pressure data, water cut, and gas-oil ratio, and some other data may be calculated. By utilizing this characteristic of the dynamic model, the model is validated. Problems arise when various combinations of history matching parameters may confirm the same set of observation data, or the model is insensitive to a reservoir parameter that is supposed to be influential. The reservoir simulation model will inherit its uncertainty from various parts of geosciences and reservoir engineering. Strictly speaking, every data source in the simulation model is associated with inherent uncertainty. Non-uniqueness is inherent to reservoir engineering and other upstream data sources, which is the root of uncertainty in upstream disciplines and simulation models. In fact, each piece of information owns its uncertainty, rendering the whole model uncertain. Therefore, understanding the model uncertainty. The uncertainty of reservoir data goes back to the fact that each piece of data in reservoir simulation is integrated with other data. For example, consider rock permeability. It is uncertain because it is controlled by various reservoir properties such as rock composition, rock types, saturations, rock compaction, layering, sedimentation, fracturing, and more, all of which are associated with inherent uncertainty. The result of reservoir measurements leads one to discover the outcomes of measurement. Each data type may share more than one of the following features and characteristics: inexact, indirect, uncertain, superimposed, partially cover the phenomenon, single source, upscaled, history dependent, correlated and propagated, prevailing phenomena observed, practical limitations. We will quickly go over a brief explanation for each of the aforementioned features and characteristics, which is helpful to understand why no data in reservoir engineering is definite. However, among reservoir data, the pressure, the temperature, the rate measurements could be assumed to be the most accurate. Inexact. The reservoir measurements are inexact because the measured results may not be reproduced if the measurement is repeated. For example, if the same set of logging tools are sent down the same well for a second time immediately after the first run, the same result cannot be recorded. However, the two results are probably close to one another, but not the same. Indirect. The measured object is not seen, and therefore the measurement is indirect. For example, to measure water saturation, electrical resistivity and other log measurements are performed. Then water saturation is concluded based on these indirect measurements. Uncertainty. The result of interpretation of the measured values to estimate reservoir properties renders the calculated results uncertain. Firstly, the measured value is inexact, and secondly, calculated results are approximate. For example, when log data is used to derive porosity, the measured log data is inexact and indirect, and also the formula used to estimate porosity is approximate equivalent for the actual rock in the reservoir pay. Superimposed. Most, if not all, of the measured values are products of many factors affecting the value of the property intended to be measured. For example, when measuring resistivity for estimation of water saturation, the value of measured resistivity is controlled by many uncertain factors, in addition to the amount of water in the pore space. Alternatively, in well testing, a specific feature is the result of many reservoir parameters superimposed, creating the diagnosed feature. Partial coverage. The acquired data does not cover the whole reservoir. If the property is measured in wells, it normally covers a small part of the reservoir. If measured by waves, such as seismic, it does not cover the whole reservoir with the same accuracy. Even in the same well, the measurement accuracy is not the same for the entire interval under investigation. Core data may be acquired from some wells and in some intervals. Single source. There is one source of measurement for each data to measure. Therefore, there is no chance to measure one property by different sources for verification of the results. Upscaled. The measured data is upscaled to a certain packet in nearly any reservoir measurement. For example, in log measurements, the minimum resolution is 0.5 feet. When data applies to the model, it must be scaled up and averaged, even if the measured values cannot be used as they are measured, because the system is discrete and can only be defined in the context of the grid cells. History dependent. The majority of data, such as saturations, pressure, transmissibility, productivity indices, rates, are all history dependent. When once measured, shortly after it changes. Correlated and propagated. Almost all reservoir data is propagated, correlated, generalized, and estimated. The reason is that there is not measured data available at every arbitrary point in the reservoir. Therefore, at any point, the data from measured points must be propagated, generalized, and estimated. Prevailing phenomena observed. In reservoir measurements and data acquisition, the dominant phenomenon or characteristic is detectable and is measured. For example, when the resistivity of an interval is measured, only the easiest path or route is pertinent to the electrical current and therefore is detected by the measuring tool. Alternatively, in well measurements, only contributing parts of the well at the time of measurement could be measured. Practical limitations. There are limitations all around: time, cost, accuracy, and depth of investigation. And mathematical formula is used to define natural processes, computational facilities, and so on. Such limitations apply to any data acquisition and interpretation process. The reservoir data with the above characteristics reveal that no data can be precisely determined. the only thing that can be done is to try and get closer to the dominant feature of the phenomena at any given time. Reservoir engineering is an inverse problem. On the other hand, the reservoir data of any kind is uncertain. In such problems, the simulation model is used to adjust reservoir data during quality control, consistency checks, and history matching processes. In fact, the reservoir response is used to estimate the reservoir data. Handling such a subtle issue requires professional experience and understanding the dominant reservoir characteristics. With the uncertainty in all data to conduct a reservoir simulation, the salient question is how to handle the reservoir simulation uncertainties to complete a reliable study. This issue is fundamental and is a complicated problem in reservoir simulation. However, in short, to have a reliable reservoir simulation model, one needs to walk with the evolution of the reservoir modeling process. This means the first should come first. Static reservoir simulation and modeling is started by geophysical interpretations to come up with a preliminary reservoir structure model. The geophysical model is associated with a relatively broad uncertainty avenue. A significant part of this uncertainty may be resolved by application of geological definitions, techniques, and information. The extent of revisions in the model by geological information should not cross the lines of consistency in geophysics. Utilizing petrophysical interpretation results in the model provides the next opportunity to make the model more precise and accurate. But again, this may not cost the coherency of the geological and geophysical interpretations. In the same token, the result of the reservoir engineering studies should be utilized in the model to make the model more precise by working inside the uncertainty avenues without crossing extreme lines of consistencies established earlier. As such, the main part of the static reservoir model is received from geoscience and some added from reservoir engineering studies. In fact, geophysics initiates the geoscience studies completed by geological studies, tuned by petrophysical evaluations, and further enhanced by the incorporation of reservoir and production engineering data. At each of these steps, complete consistency in the reservoir model is focused. The reservoir model, to be nearer to the core disciplines, geophysics, geology, petrophysics, reservoir engineering, and production engineering, is relatively more diverse with a wider avenue to be uncertain. Therefore, at any developed stage, one must work in the uncertainty avenue of the previous stages to make the reservoir model more accurate and targeted. The accuracy, however, is a relative term, depending on the extent of the data available. Having more precise and abundant data allows for a more accurate model. During the history matching process, the well performance cannot be initiated by adjusting the characteristics of the well or limited region around the well. In fact, the well performance is the result of the reservoir properties, feeding and supporting the well to perform as it performs. Controlling the well may affect the well performance, but only within a short time. Trying to match the well performance by controlling the properties of the well or a limited region around the well is the biggest mistake committed by amateurs in reservoir simulation. If matched in the short time, it deviates sooner or later over a longer period. Reservoir rock and fluid properties, which are supporting the well performance, appear in combinations in reservoir simulation governing equations. However, changing the parameters to match the performance is not arbitrary. One should not alter a matching parameter unless it could be justified in the context of the discipline in which it is determined. Being excited about packages making so-called automatic history matching is meaningless, unless it is used in the context of a professional framework to speed up the task. Field history matching can be demonstrated when wells are matched to their performance under certain matching criteria. However, for the history matching process, one must work on a global scale, field or region scale to reach local well scale objectives. Nevertheless, one may use well-related or near-well region parameters as a fine-tuning tool only. This should be the last stage of the matching the history of the wells. Last but not the least, the recorded well performance history, well rates, observation data, well pressures, productivity indices, and the like should not be assumed as the whole truth. Such data must be critically quality controlled, verified, and thoroughly checked for consistency before embarking on a history matching process. I would like to thank Nabi again for his cooperation in this episode. In the next episode, we're going back specifically to coring and looking at specialized coring hardware.